Hello. This is video number 28. And I know I said I wasn't going to post any more videos before Thursday so you could work on your binary search tree. But I also said that I was going to post a video about the remove function for the extra credit. And I never did do that. I've just been eaten alive with all the fun things there are to do for Module 2. So this is the promised video for the remove function. Remove from BST. Now, this is strictly extra for experts, extra for extra credit. So if you're not interested in the extra credit, you don't even have to take notes on this video. You don't even have to watch it. We'll wait a second for those that are not interested to leave the room. Okay, and we're back. Let's say that you are taking a shot at the extra credit BST remove function. And let's also say we've got a tree, and I meant to write this video in advance, but let's say the data that's going into this binary search tree is as followed, as fast as I can write. DUC, BOP, BOB, BUZ, and POT, LEG, FRO. This is just pretend data, no significance. HAM, SLI, SAR, REX, ROL, and WOO. Now then, we might as well, since we got to do it anyway, we can practice building a binary search tree. So here's the root. The root is initially 0, and I'm not going to fill in the external nodes. Just imagine all the little squares hanging off. We'll just look at the internal nodes, focus on those, because those are the only ones that really matter in our tree algorithms. Here we go. We'll insert these. Duck is the first one inserted. DUC with left and right pointers out. BOP is less than duck, so it comes over here to the left. BOP. Left and right, and of course those will be zeros, but there's, in the interest of time, I'm not going to put zeros or the little squares hanging off. Bob is less than duck is less than bop, so Bob is over here. Check. Buzz. Buzz is less than duck but greater than bop, so Buzz is here. Pot. P is greater than D, so pot is over here on the right. Leg. Leg is greater than duck but less than pot, so leg is here, back to the left of pot. Fro. Fro is greater than duck, less than pot, F, less than leg, so fro is over here to the left of leg. These are alphabetical order, by the way. I guess that goes without saying, huh, because I didn't say it. Ham. H is greater than D, H is less than P, H-I-J-K-L, H is less than L, F, A, B, C, D, E, F, G, H. H is, ham is greater than fro, so ham is to the right of fro. Sly. Sly is greater than duck, greater than pot, so sly is over here, to the right of pot. Sar. Sar is greater than duck, greater than pot, less than sly. So Sar is back over this direction, to the right of sly. Rex. Rex is greater than duck, greater than pot, QRS. Less than sly, less than Sar. So here's Rex. Roll. Roll is greater than duck, greater than pot, less than sly, less than Sar. Roll is greater than Rex. One more. Woo, W-O-O, greater than duck, greater than pot, greater than sly. So woo is over here. Now then, does that match the tree that I made? Yes, it does. How was I able to redraw the tree without looking at my picture? Well, a quick note here. I had this picture drawn on paper, and what I did was when I was creating the data file so I could reconstruct the tree and know exactly what it was supposed to look like, I went through and did a pre-order traversal, also known as structural order. Structural in the sense that if you insert all the things in the order that they would be printed out by a pre-order traversal, it will reconstruct your tree. Think about that real hard. If you were, for example, to try to use an in-order traversal, then when you constructed your tree, it would degenerate, and that's the word that's used. It would degenerate into a singly linked list where everything was off to the right. Try it and see. If you insert all of these things in alphabetical order, it's not even really a binary search tree anymore. It degenerates into a linked list. So to reconstruct a tree, and now I'm repeating myself, and that's not even what we're here for. Reconstruct the tree, all I got to do is dump all this stuff out to a file. This is a pretend input data file in pre-order, and then when I read them in, I can reconstruct the tree one node at a time, and it looks just like it did before, the last time I ran the program. Now then, this stuff is now officially in the way. The data, by data, close the file. That was the official closing of the input file. What we want to do is remove, and I'm going to do this by cases. Not all cases are created equal. Some of them are quite a bit simpler than others. Case number 1. Let's remove Jack. These are cases of remove, by the way. All of them are remove. Jack, J-A-C. Okay? J is greater than D. H-I-J-K-L, I'm going to put. J is less than P. It's come back this way. H-I-J-K-L. It's less than leg. It's greater than fro. H-I-J-H-I-J. It's greater than him. But look, we run into, there is where a 0 will be. We're searching for Jack so that we can remove or delete Jack. And there is no Jack. So case 1 is, it's not even in the tree at all. This would return false. I told you, some of them are pretty easy. If it's not there, it's easy to remove. 2, moving up in order of complexity, let's remove, who do we want to remove? Let's remove Buzz. See if we can get rid of Buzz. Buzz is less than DUC, greater than Bop, and ding ding, we found Buzz. Here's Buzz. Now we got to remove Buzz, but Buzz has no internal children. Both of these are external nodes, meaning they're really just 0 pointers. So it's almost like it's the last node in a list or something like that. It's off the bottom of the tree. To delete Buzz, boom, Buzz, you're gone. Delete and reset this pointer up here to a 0. I will write in that 0 because you don't want to leave that dangling pointer. It's a ghost pointer. After you delete node Buzz, then there will be no node that this points at anymore. So that will return true. The return value is almost an afterthought here, but I'm still putting it up here anyway. So we would just delete Buzz and set the pointer to Buzz to a 0. Case 2. Case 3, moving right along. Who do we want to whack this time? Let's get rid of leg. L-E-G. L-E-G. L is greater than D, move to the right. L is less than P, move to the left. There it is. There's leg. Now leg is a little more complicated because leg does have one internal child. It only has one, so it's not absolutely horrible, but it's medium horrible. So what we do if we run into a node that we're trying to get rid of, do the remove function, and it has one internal child, then the procedure is, the surgical procedure is, replace the node you're deleting with its one internal child. It's almost like the bypass operation we used to do with singly linked list. It doesn't even matter whether fro down here has a whole bunch of kids left or right. It doesn't matter. If leg, and where it is in the tree, if it only has one kid, then you move this up. Replace leg with fro, which is going to have the effect of making Pot's left child pointer point at fro. That was a mouthful, even with 3-letter words. If you find what you're looking for, and it has one internal child, which leg had one internal child, then to delete it, you put a temp pointer on it. It really is like deleting a node from a singly linked list. You make a temp pointer point at this, and then you do the bypass thing. Pot's left will no longer point at our leg pointer leg node that we're about to delete. We bypass that and make Pot point to fro as its left child. And it's going to be a very similar operation, of course, if it's a right child rather than a left child. Okay? Done and done, that would return true. 4. You knew it was coming. Let's get rid of pot. You know, just to try to make this as painless as possible, I'm going to say that we did delete leg and we closed up the gap. So now this is what the tree looks like. It's going to be messy enough as it is. What's the deal? We got to be able to remove any node that's in the tree. We can't just say no, return false. That would be nice, wouldn't it? No, that's going to be too difficult. I'm just going to return false. I'm going to leave that in the tree. Okay, no, can't do that. Pot is greater than duck. There it is. But look at pot, good grief. It has a non-trivial subtree to the left, a non-trivial subtree to the right. Oh, woe is us. What are we going to do? Listen to this carefully. If it's got 2 internal kids, in other words, both of these pointers are non-zero, they both point at something, then what we're going to do is replace this node with what's called, I'll use a different color, new terminology. It's in-order successor. I-N-O-R-D-E-R, successor. S-U-C-C-E-S-S-O-R. It's in-order successor, which is easy to describe. That just means it's the very next node after pot that would be printed out if we were doing an in-order traversal. And the in-order traversal goes left and right, so Sly would be the next thing printed out. Absolutely not. In a pre-order traversal it would be, but think about this. The in-order traversal swings around. After it's printed all of this, it will print out duck, and then it doesn't even print out pot immediately. It prints out all this stuff over here, then swings through, here comes pot, then it prints out pot. Then the next thing the in-order traversal would print out would be way down here, Rex. Look at that. They're not even close to each other in the tree. And Rex has its own problems down here. What is that? Oh, that's an R. Look like Vol. Go Vols. It's R-O-L. That's so I can read it. Okay. The in-order successor, let me say that again. The in-order successor of pot is the next thing that would be printed if we were doing an in-order traversal. And in this particular tree, that would be Rex, which is a non-trivial case of delete that we've already looked at over here. So somehow or another, we got to replace pot with Rex. Okay? Now, before I even talk about the replacement, how do we look at the in-order successor without doing an entire in-order traversal? Listen to this. It's like giving directions to get to the grocery store. Go to the right once, go to the left until you hit a 0 pointer, an external node. The last internal node you saw on the way to that 0 pointer is your in-order successor. Let me show you what I'm talking about. Who is pot's in-order successor? Go to the right once, because it's going to be greater than pot. Go to the right once, go left and left and left until you can go left no more. Don't go to the right down here. We go to the left until we run into a 0 pointer. And there, ladies and gentlemen, that will be the next node. I'll even circle it. That will be the next node that's printed out by an in-order traversal. That's why it's called the in-order successor. One more time. Go to the right once. Go to the left, 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 until you run into a 0 pointer. And the last node, before you get to the 0 pointer, before you fall off the edge at an external node, that is the in-order successor. Okay? Now then, what do we do with that? Well, we just copy the data. Whatever the value type object is that's stored here in this node, copy that into the node that we're deleting. So we don't even really delete the node at all. That just seems too miraculous to be true. So I'll copy Rex up here. But, it's 2 parts. Now that I've done that, and I didn't even delete a node, Rex is actually the one that gets whacked. We can't allow duplicates, so now that we've copied Rex up here, Rex has to go. And Rex is going to be at worst a case 2 or a case 3. Why? Why can't Rex be another horrible complication on top of complication, and it's another case 4, a node with 2 internal kids? Well, it can't possibly be because of the way we chose the in-order successor. I mean, the definition of in-order successor, it's got to have a 0 pointer here. It might also have a 0 pointer over here if roll hadn't been in the tree. So it could have been case 2, where there are no internal children. At worst, it's a case 3 with one internal child. So what's going to happen is Rex does get whacked, but it's a case like the one I erased over here. Roll closes up the gap. So what we'll have, I'll just bend this left child here. Roll is now the left child of SAR. So we did delete a node. Oddly, though, we didn't delete the node that held the data value that we wanted. Oh, and this one's going to return true. Why do we have to go to all those contortions? We've got to preserve the binary search tree nature of this. In other words, we can't just arbitrarily delete nodes and put new nodes in their place. It still has to be a binary search tree. How do I know it's a binary search tree? Well, I'll pretend I've already printed this stuff out over here. And let's proceed from duck with our in-order traversal. It should print out, after duck, it should print out fro, then ham, then rex, then roll, then SAR, then slide, then woo. And you'll have to play that part of the video back and make sure that that's in alphabetical order. If I did this correctly, then it's still in alphabetical order. You know what? This is bothering me. I'm sorry. Got to pull roll up here. There! Now you look like a proper left child. There. And that should be a binary search tree. And that is all possible cases. All the things that can happen. And you might think about that. Well, of course, four possibilities, zeros and ones. 0, 0, 2 external nodes. 0, 1, 1 internal node. I don't know where I'm going with that. I lost my place. Though it's 0, 1, and 1, 0 are both the same case. Scratch that. No mapping to binary numbers. 1, 1, it has 2 internal kids. Okay. I should have quit while I was ahead. Now it's too late to quit while I'm ahead, but I'll just quit anyway. See you online.